Thanks, Dave. Yeah, so it's joint work with Ilan from Renato and Adrian from MIT. It's going to be maybe next week. So let's talk about this problem called multidimensional binary search. And that's a task in online learning that comes up very frequently in problems in pricing, especially like online pricing with contextual information. So I'll start by describing to you what multidimensional binary search is, and I'll start with the usual binary search that you already know, but let me just remind you. In binary search, there is an unknown quantity theta that's between 0 and 1, and you want to guess this quantity. So you're allowed to submit multiple guesses, which will be some xt, and then I'll give you feedback saying, is that too large, is that too low? So my feedback is xt is larger than theta or smaller than theta. And I want to count your mistakes. And by a mistake, if you guess epsilon away from theta, I'll tell you make a mistake. If you guess epsilon close, you're fine. And you want to bound the maximum number of mistakes you can ever make. And that's, a simple task. You don't know how to solve it. So let me just describe to you the optimal policy. You start by, one way to describe is that you start by something like called a knowledge set. A knowledge set is what you know about theta so far. So right now, you know that theta is between 0 and 1. So your knowledge set is the interval 0, 1. And a natural guess that guesses the middle point. You guess that it's 1/2. Then you get a feedback. Maybe your feedback says theta is smaller equal than half, greater equal than half. And then you update your knowledge set. Now your knowledge that theta is between 1/2 and 1. Guess in the middle. Get feedback, say theta is smaller equal than 3/4. Continue. And you keep doing that until your interval is like epsilon. At that point, you localize theta to within the precision you want. And then you are done. Then from that point on, you log 1/epsilon steps, you don't make any mistake anymore. It's okay, so that's it and that's necessary. You can easily prove that you cannot do better than log 1/epsilon. So far so good. So let's make it slightly more interesting. Let's make it multidimensional. Now instead of unknown quantity, unknown number, you have an unknown vector. So unknown vector theta in d dimensions. And I also normalize, say that it has norm and most 1. And I also keep asking you to guess, but what you're guessing is a dot product. So I'll adversarially pick some direction, some unit vector ut, and I'll ask you to guess what's the dot product between theta and ut. So our guesses would be some xt, and I'll give you the same feedback. Is your guess larger or smaller than the dot product between theta and xt? And this problem is the same. You want to bound the number of mistakes you can ever make. So if you guess far away from epsilon, you make a mistake. If you don't, then you're fine, and you want to bound the maximum of mistakes you can ever make. And this comes up in a lot of applications in online learning for pricing, which I'll talk later. But let me tell about an application that actually is exactly this problem. That's it's getting quite popular in medicine, actually, and I'll pick it up by some OR papers. Bastani and Bayati had this really nice paper about this problem called personalized medicine. And the story they tell around this issue is just that you want to develop drug dosage that's for each patient. So each patient arrives, they need different dosages of the drug. Each patient is a vector of features. Say they tell the genetic information, the age, some other health information, whatever, and then you want to find how much of the drug you need to give him, and you assume it's some sort of dot product between theta and some ut, but you still don't know theta. So if the doctor comes, the new patient comes, each patient is different, then the doctor says some amount, and then he observes if the patient, after taking this drug, he was overdosed or he was underdosed. And then he can update. For the next patient, he can try something else. But the next patient will be a different person, so he needs to sort of adapt. And that he wants to bound the number of times he would take until you get, until your dose is epsilon away from the optimum. Right? So what do we know about this problem? So the first, that there is a simple lower bound. You cannot get better than d log 1/epsilon, in particular because the problem can contain d-independent binary searches, single-dimensional binary searches. And the way that you can, your context that you can get, they can be all the coordinate vectors. If your context ut is a coordinate vector, then pretty much you need to guess the ith component of theta. And then for each of them, you need to do log 1/epsilon, so you need to take at least the log 1/epsilon mistakes. So that's good. So what do you know with the upper bound? So last year in EC, Ilan and Maxime Cohen and we had this paper that's about the pricing problem, that the main component was actually solving this binary search problem. And we gave a d square log 1 over an epsilon mistakes bound. And what we do in this paper is that we make it tight. We remove this square. But what I thought was interesting, actually, the way that you take to remove the square, which actually so let me tell you how that's made. But before, let me actually tell you about what the ideas in the score and Lobel and myself paper last year. Right. So what they do is that it's pretty similar to the original binary search. You start just skipping knowledge sets. Your knowledge in the beginning is that theta is in the unit ball. So let's say that's what you know about theta in the beginning of time. And then you get a context. So context would be like a vector ut. And then after you have the context and you have your knowledge, you can see what's the maximum possible guess that makes sense, what's the minimum possible guess that makes sense, the maximum, the minimum of the dot product over your knowledge set. And after that point, you can ask, is the difference between the maximum possible guess and impossible guess larger or smaller than epsilon? If it's smaller than epsilon, I'm fine. I already know how to localize epsilon to x to epsilon error. If not, I need to guess something in between. Maybe I'll make an error. So a guess will correspond to a line. And then you get a feedback. Maybe they say that it was larger, it was smaller. And then you can rule out one side of your knowledge set. Pretty much you update kt plus 1 to be whatever you knew, plus the dot product smaller than your guess or larger than your guess. Depends on what was the feedback. Okay, so the first thought that we had is that still like binary search. Like take the midpoint, compute the maximum, the minimum, take halfway. But that's, you generate too many errors. You need 2 to the d log 1 of epsilon errors. So that's not nice, but then we find some way that generates d square, which is polynomial, so we're happy. And the idea is this idea of ellipsoid pricing. The idea is kind of simple, but actually it's nice, it works effectively. You get this set that you have, but instead of fusing that, you augment it a little bit. You take the minimum enclosed in ellipsoid, and then once you get that to be your new knowledge set, once you got new direction cut through the center, take half, also go to the just enclosing ellipsoid, and continue doing that until you have an ellipsoid of epsilon radius. And if you do the analysis, it goes to d square log 1 of epsilon. So why d square? And the reason is d square and not d is because ellipsoids, they shrink very slowly. If you cut your set in half, you go to half your volume. But if you, after that, you expand your ellipsoid to be, you add this ellipsoid, you see that the ellipsoid is like a little more than the original set. So it will actually add some more volume, and that's actually worse the higher the dimension. So the new knowledge set will be e to the minus 1 over d of the new volume. So you take d square log 1 of epsilon steps to get to volume epsilon to the d, which is what you want of a ball of radius d. And ellipsoids are also nice because what you care here is not really volume, you care about radius. So ellipsoids are nice because ellipsoids have these very nice descriptions that you can represent them in terms of eigenvalues. You can sort of control how relate length or volume. So they're really nice. But still there's this d square that's d away from the tight thing. And by then, if you had asked me last year, can you do d? And I said, here's what the story I will tell you. I'll tell you, I think we can do it. There's a natural way, just like don't do this regularization. Just like cut in half, don't do the ellipsoid. And I will tell you, I don't know how to analyze that because after I don't do the ellipsoid, I don't have this nice description. I have this crazy shape that I don't know how to deal with. I don't know how to bound length or volume and so on. But it probably works. But you need to find some way to sort of control the shape. That's what actually we set to prove 1 day later, but it turns out that actually that doesn't work. Halving the ellipsoid only also takes d square. And let me present you intuition why. Let's say that you at some point, you end up your set being something like that. Sort of a very elongated pyramid. So in this part here, it's all epsilon, it's all tiny, but you have one big direction over there. Let's say you get a context UT like that, and you try to halve the volume. But if you have a cone or a pyramid, like that, most of the volume will be next to the base. In particular, it will be like 1 over d here. So we do really slow progress towards like shrinking that. In particular, you need d log 1 over epsilon steps just to get rid of that one dimension. But now you can do that recursively. Each dimension needs k log 1 over epsilon to get to shrink it to size epsilon, so you get d square log 1 over epsilon. That's okay, that's a bit disappointing because it's the new algorithm that gives you the square log 1 over epsilon, you need to want to get d. So here's the idea. The idea actually comes out of this picture. So what's the issue here? The issue here is that you have already some part which is tiny, like this base of the pyramid, and you have this part which is big. And you want to shrink it to epsilon. And the reason we're so slow is because what's dragging you down is the other dimensions that are already fine. These dimensions are okay, you know how to deal with them. And somehow their shape is the fact that they are a pyramid and not a cylinder is dragging the algorithm. So what you do is like there is a natural way to solve this, and is make it a cylinder. So there is this new regularization technique that's called cylindrification, and that's this. I have a formal definition here, but I will show you a picture. So you have this shape here, and let's say you have some direction. Let's say S1. So one way to make it a cylinder with respect to S1 is that I project my shape into this direction S1, and I project my shape into the orthogonal direction of S1. And then I take the sum of those things. And I could do for multiple things. I can project into some dimensions, I can project into orthogonal dimensions, and I get the cylinder. And the idea of making things a cylinder is that some dimensions are already fine. You know that you already want them, you already shrink them to epsilon size. And for the remaining, I just want to work on the other dimension. So I'll make the dimension that I already want very simple as I can. So that's the idea of what cylindrification is. Right, so let me give you some notation before I give you the algorithm. I'll define the width of a shape. Okay, so my next step, I'll just tell you the entire algorithm that uses cylindrification to solve this problem as the tight regret. So given this set, I'll call in a direction I'll call width, pretty much like how big it is, the uncertainty that I have. And also given a convex shape, also if I define the centroid as just that integral. And the centroid has this really nice property given by this Grunbaum theorem that if I take any hyperplane through this point, it always divide into at least the volume will be 1 over e in each side. So it will be a balanced sort of separator for whatever hyperplane I put it here. Right? So now I can define the algorithm. And the algorithm is actually simple. You just always predict the centroid, pretty much, with one twist. So whenever you have a direction ut, compute the centroid, predict the dot product between the centroid and ut. Then you update a knowledge set with 2 more, and that's the new 2 bullets are the new things. So what you do is after you have first you check for thin directions. If there's some direction that now becomes too thin, that you know that already made a lot of progress in that direction, you add that to some set. If there's okay, and after you have a set of directions that you already know that already is small, cylindrify your current set with respect to those directions. So that's the algorithm. If you spend time with convex geometry, you know that all of those things are NP hard to move, but they can be made computational with some more work. You can sort of implement this, not exactly this, but this actually gives you the right regret. You can get also the right regret in polynomial time but I'm not going to talk about that. Instead, I'll just say the theorem, if the delta is small enough, then the algorithm gets you the log 1 of epsilon regret. And the intuition is this one that I said. Like, you have 2 directions, you know they're small. When you cylindrify, this becomes something like this. And out of a sudden, you can get, instead of taking d log 1 of epsilon, because the other dimensions are dragging you, just doing log 1 of epsilon. So per dimension, you do log 1 of epsilon. Okay, so how does the proof goes? I mentioned that I cannot make progress by tracking the volume. So instead of tracking the volume, I'll start tracking the volume of the projection. But that's actually, there is some technical difficulties because this Grunbaum theorem that I described that you can cut through the centroid, it gives you, it says that the volume of the whole set splits in a constant fraction, but doesn't tell you anything about the volume of the projection. So there are two actually main technical difficulties here. One difficulty is obtain the Grunbaum for the projection. So show that what kind of proof bounds on what happens with different projections of your set once you cut through the centroid with the volume. And the other thing is this called cylindrification lemma. That either you cut to the centroid and you can use the first part, or you add a new dimension to your, you add a new direction to your set of small directions, and then you want to relate the volume of the projection, the volume of the original set. And that could be pretty bad, but if it turns out that this dimension is thin already, it is not so bad. That's what's called this cylindrification lemma. But I just want to flash it to see like some of, if you're interested in like, if you have problems in price that turns out to involve like convex bodies and cutting two directions, you might have find a lot of useful geometric lemmas in this paper. But I want to end up the talk by describing the application that got us to start thinking about this problem. That was the application, that was the main thing in the paper that we presented last year in EC. And that has been like studied by a couple of different people. And this problem of like online pricing with feature vectors. In this problem, you get products online. So each product is described by features, say the color of the product, the size, different things. So each product is a vector in RD. And you assume there is a buyer whose valuation is a dot product, theta transpose UT. And once you get this product, you need to quote a price for this. You quote a plus price PT, and then you learn if this product was sold or not. So what is, using this multidimensional binary search, you get a d log t regret for this problem. And so that's actually my last thing. I'll just end up the talk saying an open problem. I think here, pretty much the binary search problem, I think at this point is solved. You have tight bounds. You could maybe try to make the running time less horrible because it's the running time is made polynomial in this paper, but it's still like d to this big power because you need to compute all the centroids and things. But what I think is really the nicest problem is actually making this problem tight. So binary search is the d log 1 of epsilon is tight, but for the pricing problem, we don't know. In particular, there is this, the only lower bound that we can prove is d log t. And the reason that doing binary search for pricing is slightly different than binary search, the usual binary search. You just want to count mistakes. Because quoting a price that's too low, you don't make you don't get 0, 1, you can get like most of your price if your price too low. And so it's a very symmetric problem, and that makes it very hard to reason. So Kleinberg and Leighton had a really nice paper that they solved the one-dimensional problem. So that for one dimension, they do log t regret, and that's tight. Then for d dimensions, you again can construct a similar lower bound because you can, all your contexts are coordinate directions, so you could have like the independent versions of this problem, so you need at least d log t. But we don't know if, in some sense, like I spent quite some time trying to adapt this algorithm to d dimensions, but it seems like many things about this algorithm use the fact that it's one-dimensional, pretty much. The thing you're trying to guess is pretty much similar to your knowledge set. And here, so I don't know, if I were to guess, I would guess that, I actually I don't know how to, so my guess would be that the dimensions, like once you go to 2 dimensions, is already different. You need, at least you need new ideas. So I just want to end up leaving this open problem. Thanks.